Let's now discuss the influence of opens and shorts inside series circuits. First, let's examine opens. Consider the series combination of A, B, and C, where there is a gaping hole between A and B. This is an open circuit. An ohmmeter demonstrates that this series combination of three elements, including an open, now presents an infinite resistance because no conductive path exists. Consider the open being relocated between B and C. Again, the ohmmeter demonstrates that this series combination of three elements, including an open, now presents an infinite resistance because no conductive path exists. In summary, an open anywhere in a series path completely severs that path. It makes sense. A series or inline path with a rupture or open anywhere in that single path does not have a conductive path. Let's now deal with shorted elements in series circuits. A short is a low resistance around or in parallel with an element. Consider resistor A, ordinarily a resistance of roughly 220 ohms, with a 0 ohm wire in parallel, or around it. Think about it. When presented with a 220 ohm path or a 0 ohm path, through which path would a majority of electrons travel? Undoubtedly, the 0 ohm short presents a far easier means of travel from end to end. The ohmmeter confirms this fact. Shorted resistor A now presents a small resistance path. If we include shorted resistor A in the series combination of all three resistors, the ohmmeter demonstrates the total resistance of the series path is now only the series combination of B and C, implying that shorted resistor A is essentially excluded from consideration. What happens if we return resistor A to its original configuration and short resistor B? The ohmmeter demonstrates the total resistance of the series path is now only the series combination of resistor A and resistor C, implying that shorted resistor B is essentially excluded from consideration. In summary, a shorted element in a series path removes only that shorted element from consideration. Let's now examine parallel arrangements of resistors. See if you can calculate the total resistance of A in parallel with B, B in parallel with C, and finally A, B, and C all in parallel with each other. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. The parallel combination of A and B should present a total resistance of approximately 133.5 ohms. The parallel combination of B and C should present a total resistance of approximately 194.5 ohms. And finally, A, B, and C, all in parallel with each other, should present a total resistance of approximately 104.0 ohms. In each of these occasions, note how the total resistance of a parallel combination is always smaller than the smallest resistor. Let's use the ohmmeter to verify these theoretical calculations. When placed between the probes of the ohmmeter, the parallel combination of resistors A and B appears to present a total resistance close to our theoretical calculations. Similarly, when placed between the probes of the ohmmeter, the parallel combination of resistor B and resistor C appears to present a total resistance close to our theoretical calculations. Finally, when placed between the probes of the ohmmeter, the parallel combination of resistors A, B, and C appear to present a total resistance close to our theoretical calculations. You'll note the order of parallel elements does not influence total resistance. For example, the parallel combination of A, B, and C would present the same total resistance as would ACB, BAC, CAB, or any other possible permutation of A in parallel with B in parallel with C. In summary, the arrangement of individual resistances does not influence total resistance of a parallel arrangement in any way, shape, or form. Let's now discuss the influence of opens and shorts inside parallel circuits. First, let's examine opens. Consider the parallel combination of A, B, and C, where A is dangling out in space. The ohmmeter demonstrates that this parallel combination now presents a total resistance equivalent to only resistor B and C in parallel with one another. It makes sense, because resistor A is not really in this parallel circuit. Consider the parallel combination of A, B, and C, where now resistor C is dangling out in space. The ohmmeter demonstrates that this parallel combination now presents a total resistance equivalent to only resistor A and B in parallel with one another. Again, it makes sense because resistor C really isn't in this parallel combination. In summary, an opened element in a parallel configuration removes only that opened element from consideration. Opens can occur in other places in parallel circuits. Consider the parallel combination of A, B, and C, where the entire parallel combination is dangling out in space. The ohmmeter demonstrates that this parallel combination now presents an infinite resistance because the open has severed any and all paths through everything. Let's now deal with shorted elements inside parallel circuits. A short is a low resistance path around or in parallel with an element. As previously, consider resistor A, ordinarily a resistance of approximately 220 ohms with a 0 ohm wire in parallel. The ohmmeter demonstrates shorted resistor now presents a small resistance path. If we include a shorted resistor A in the parallel combination of all three resistors, the ohmmeter demonstrates the total resistance of the parallel combination is now extremely low, implying that shorted resistor A is effectively shorting out the entire parallel combination. What happens if we return resistor A to its original configuration, short out resistor C? The ohmmeter demonstrates the total resistance of the entire parallel combination, including a shorted element, is now extremely low, again implying that a shorted resistor C has effectively shorted out the entire parallel combination. In summary, a shorted element in a parallel configuration effectively shorts out the entire parallel combination. Moving on. Recall that the element being measured by an ohmmeter must be depowered and must be removed from a circuit. Let's use a different type of circuit to demonstrate this fact. Consider a series parallel combination of resistors A, B, and C, where resistor A and B are in parallel with one another, and this parallel combination is in series with resistor C. One can simplify the original series parallel circuit as an imagined resistor R single prime being the parallel combination of RA and RB in series with resistor C. The parallel combination of resistor A and B presents a resistance of 133.5 ohms. The total resistance of this series parallel circuit is our imagined resistor R single prime in series with resistor C. When our imagined resistor R single prime is taken in series with resistor C, we might expect the total resistance of this series parallel combination to be 604.5 ohms. The ohmmeter confirms this fact to a reasonable degree of accuracy. Note resistor A and B are in parallel with one another, and this parallel combination is in series with resistor C. Let's use this circuit to examine the measurement of resistances internal to a larger circuit. If we wanted to use the ohmmeter to check the resistance value of individual resistor A, still inside the series parallel circuit, the ohmmeter reads an incorrect value of roughly 133 ohms. 133 ohms? I thought resistor A was a 220 ohm resistor. Why is the ohmmeter giving us bad data? I'll tell you why. The ohmmeter is being used incorrectly. To measure the resistance of an individual element, that element must be removed from the circuit. You know that the ohmmeter is reading the parallel combination of resistor A and B, and not just the resistance of A, as we intend. In order to measure the resistance of just resistor A, we need to isolate resistor A by removing one or both terminals from the circuit. With resistor A effectively isolated, the ohmmeter now reads just the resistance of resistor A and nothing else. In summary, an element must be isolated from the circuit for an ohmmeter to obtain a valid resistance reading. Another complication exists when isolating elements from a circuit. Consider a DC power supply attached to resistor A. Even in the depowered state, this source will improperly influence resistance measurement because an unseen internal resistance through the source. If you want to think of it this way, imagine the source's internal resistance as an unseen resistor in parallel with resistor A. When the ohmmeter is used to check the resistance of resistor A, still hooked to the source, the ohmmeter reads an incorrect value of roughly 180 ohms. Why is the ohmmeter giving us this incorrect value? I'll tell you why. The ohmmeter is being used incorrectly. In order to measure just the resistance of resistor A, we need to isolate resistor A from the source by removing one or both terminals from the source. With resistor A effectively isolated from the source, the ohmmeter now reads just the resistance of resistor A and nothing else. Again, an element must be isolated from the circuit, including the source, for the ohmmeter to obtain a valid resistance reading. Before we bring this lecture to a close, let's talk about the lower and upper extremes of resistance measurement. At the low end of the resistance spectrum, consider a length of thick, highly conductive cable. At the high end of the resistance spectrum, consider the rubber or plastic coating of insulation surrounding a wire. Regarding measurement of these two low resistance and high resistance extremes, do you think any measurement obtained using ordinary DMM would be accurate? Not even remotely. If you required exact accurate measurements of such small or such large resistance magnitudes, one would have to use special equipment purposely designed to measure this level of detail. Such a piece of equipment would be an ohmmeter, but they'd be ohmmeters designed to handle either the lower or the upper range, not both. An ohmmeter designed to measure extremely low resistance paths, like a transmission line or a lightning rod, is unsurprisingly called a low resistance ohmmeter. whereas an ohmmeter designed to measure extremely high resistance paths, like insulation surrounding a motor winding, is called a megohmmeter. Oftentimes, you'll hear a megohmmeter referred to as a megger, after the company that makes an extremely popular line of megohmmeters. Such special purpose tools are a little above our current level of understanding right now, but we'll come back to discuss these tools in much later lectures. Right now, you simply need to be aware that general purpose DMMs in ohmmeter mode have limitations inside of which they are intended to operate accurately, and outside of which they won't. Alright, that about wraps it up for a general discussion of the DMM ohmmeter function. Remember to RTFM. Read the fine manual about your specific DMM, and always, always, always use the function, leads, range, placement checklist every time you employ it. You'll be glad you did. In conclusion, this lecture took a close look at the ohmmeter function of the Fluke 87 Series 5 digital multimeter. We discussed basic operations of an ohmmeter, audible continuity testing, and limitations and special considerations of ohmmeters. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.